Welcome to Lecture 10. In this lecture, we will begin to discuss Karnaugh Maps, which is one of the most important topics in this course. If you're following along in the book, this is discussed, or the beginning of the discussion is in Unit 5. Let's start with a little bit of terminology. If we say that A is an implicant, notice the N here. We're going to have a similar word later, implicate, that has no N in it. So do observe the A there. So if the N, if A is an implicant of B, that means that A equals 1 implies B equals 1. Now, let me give you an example here. If we had the expression f of x, y, z is equal to xy or xz, this is just an example, then xy is an implicant of f. Now, the way that we can see that this is true is that obviously if xy here, with this expression here, xy, if it's equal to 1, it doesn't matter what xz is equal to. Whether xz is equal to 0 or xz is equal to 1, we know that the value of f is 1, because if xy is equal to 1, 1 ORed with anything is still 1, and therefore, if xy is equal to 1, then f must be equal to 1. So xy equals 1 implies f equals 1, and thus xy is an implicant of f. Notice that xz is also an implicant of f. And the reasoning is the same there, because if this term here, this xz, is equal to 1, we don't care what the other term is equal to, whether it's equal to 0 or 1, f will still be equal to 1. So if we think of xz here as playing the role of a, if xz is equal to 1, then f is equal to 1. And so from this we see that xz is an implicant of f. Now let's ask, is x an implicant of f? And the answer here is no, because if x is equal to 1, that doesn't necessarily imply that f is equal to 1, because if y and z are both 0, then 1 ended with 0 is 0 here in this first term. 1 ended with 0 would be 0. 1 ended with 0 would be 0 here, and 0 ORed with 0 would be 0. So it is possible that x could be equal to 1, and yet f would still be equal to 0. And therefore, since x equals 1 does not necessarily imply that f is equal to 1, x is not an implicant of f. Now let's look at another example. Let's say this time that f of x, y, z is equal to xy, or xy prime, or let's say perhaps yz. Okay, now you might turn off the video for just a moment and try to identify the implicants of f, and then we'll resume. Okay, well, we see that one implicant of f is xy. And this is just like what we had before. If xy is equal to 1, 1 ORed with anything is 1. And so therefore, if xy is 1, f is 1, and therefore xy is an implicant of f. Similarly, xy prime is an implicant of f. And yz is an implicant of f. And now ask, is x an implicant of f? Now you remember we asked a similar question before, but be careful with your answer to this problem. Do you think x is an implicant of f in this case or not? Well, one way to figure this out is the following. You could reason as follows. You could say if, I'll come up here, if x, you remember, for something to be an implicant, for x to be an implicant of f, the proposition x equal 1 must lead to the conclusion that f is equal to 1. So let's see if that's the case. If x equals 1, then f, okay, let's just take this formula, and everywhere we see an x, let's put a 1. Well, f would be equal to 1 ended with y is y, 1 ended with y prime is y prime, and the last term, yz, doesn't contain any x's in it, so it would just remain the same, yz. Now, we see that the yz term could be absorbed into y, and so this would become y or y prime. But remember that any variable ORed with its complement is 1. And therefore, the proposition here that x is equal to 1 did indeed lead to the conclusion that f was equal to 1. So in this case, x is an implicant of f. In fact, x is said to be a prime implicant of f. Now, we'll understand much better when we get to Karnaugh Maps what we mean by prime implicant. But for right now, let's just say that a prime implicant is an implicant that has as few variables as possible in it. What I mean here is that xy is an implicant of f. Similarly, xy prime is an implicant of f, but actually it's not necessary for us to take both x and y. As we have found out here, x alone is an implicant of f. So xy would not be a prime implicant. It has more variables in it than we actually need. X is a prime implicant. So I'll just write here, let's not worry too much about this idea at this point, because it will become much clearer with Karnaugh Maps, but just for right now we'll go ahead and say, in fact, x is a prime implicant Okay? And so we've learned then the word implicant, and we've learned the word prime implicant, and now that we've learned these two words, let's start thinking about Karnaugh maps. Now, one word of explanation here. I'm going to go ahead. Let me maybe give an example. Let's say that we have f of x, y, z is equal to x, y prime, z, or x prime, y prime, z, or x prime, y prime, z prime. And we're asked to find the Karnaugh map of f. How would we proceed? Well, I'm going to do things in just a slightly different way from the way your book does, and once we learn how to do this, then I can justify for you why I would prefer to make it just a little different from what your book does. But it really is just a matter, I'm going to be rotating what your book does by 90 degrees on the page, and so if you don't like one way, then you just rotate the page 90 degrees and you'll get the other way. So let me explain. Let me give you an example. For to draw the Karnaugh map of a function, the first thing you need to know is the number of Boolean variables. And in this case, we have 3 Boolean variables. So when you have a 3-variable Karnaugh map, it's going to look like the following. A Karnaugh map is always going to be in a rectangular form, and it will always have boxes, or we'll call them cells, in it. And the number of cells in a Karnaugh map will be equal to 2 to the n power, where n is the number of Boolean variables. So in this case, since there are 3 Boolean variables, and 2 to the third is 8, we see that there are 8 cells in this Karnaugh map. Now, I choose to write a Karnaugh map for a 3-variable function in the way that I've shown here. And I will label this vertical axis as x and the horizontal axis as yz. Your book would simply do it like this. They would label the horizontal axis x and the vertical axis yz. But you can see that that's just a 90-degree rotation of what I'm doing. The reason that I like the method that I'm going to show you a little bit better is that we have a tendency, I think, to read from left to right first and then from top to bottom. And it seems to me that when you do the Karnaugh map in this fashion, there's more of a tendency to read from top to bottom and then from left to right. This is certainly debatable, and I think that well, it certainly makes no difference. It's just what you're accustomed to. But I think that I'll go ahead and stick with the method that I'm showing you here first on the left. But if you want to compare what's in the notes to what's in the book, all you need to do is just rotate one or the other of these by 90 degrees, either clockwise or counterclockwise. Okay, so the first thing we do then is we figure out the number of cells we need in our Karnaugh map, and in this case that will be 2 to the third power, or 8. And I'm labeling x over here on the left, y and z on the top, and now we need to put in some numbers. And for x, we'll put in 0 and 1. That's easy. But for the top we need to put two numbers. One number will represent the value of y, and one represents the number of the value of z. Now we start with 0, 0, as you might expect, and then we'll go to 0, 1, and you probably all expect that the next one will be 1, 0. However, that is not the case. The next one will be 1, 1, and the last one will be 1, 0. Now, the reason for this numbering scheme is the following. As we go from either a cell on the top to the adjacent cell on the bottom, or from any cell to the cell on its right, we want only one variable to change its value. So let me explain what I mean here. In this first cell, we have x equals 0, y equals 0, and z equals 0. That's here in this cell right here. Now if we move, let's say, down, then only one variable changes its value. Y and z will still be equal to 0, but now x will be equal to 1. Or if we start back in this cell where all three variables are 0, and we move to the right by one position, then x stays equal to 0, y stays equal to 0, but z changes from 0 to 1. So again, only one variable is changing its value. Now suppose that in this third column, instead of having a 1, 1, we had put 1, 0. Well, then you notice that as we move from this cell to this cell, both y and z change their values. X doesn't change, it's equal to 0 in both of these cells, but in this cell, y is equal to 0 and z is equal to 1. In this cell, y is equal to 1 and z is equal to 0. So both variables change their value, and we don't want that. So that's why we make this column the 1, 1 column. Now, another thing you need to know about the Karnaugh map is that although it appears to be just a rectangle, actually its right-hand edge is connected. We should consider it to be connected to its left-hand edge. So for instance, if we're right here in this cell, we can move right, and where we will go if we move right from here and move to right, we'll get to here. And likewise, if we're here and we move right, we'll get here. So and similarly, if we're here in this cell and move down, we'll go to this one. If we're here and we move down, we go to this one. So in other words, you need to think of the top edge being connected to the bottom edge and the right edge being connected to the left edge. Or in other words, this, if you think of joining the top to the bottom, that would give you a tube, and then if you connect the two ends of the tube, you have a donut. So this is actually a donut, or some people call it a torus type of a structure. But just remember that the top edge is connected to the bottom edge, and the right edge is connected to the left edge. That is always true in any of our Karnaugh maps, not just 3-variable Karnaugh maps, but even in a 2-variable or 4-variable Karnaugh maps. We're going to look at Karnaugh maps in all of those cases, and in each case, the top and bottom edges should be thought of as being connected, and so should be the right edge and the left edge. So now that we have actually drawn the basic structure of the Karnaugh map for this function, now we need to fill it in. And this function, the way to fill it in is the following. We want to look at each cell. As I said before, each cell represents one of the particular situations, you might say. It gives you a value for each of the variables. So for instance, right here we have x equals 0, y equals 0, and z equals 0. And so we fill into that cell the value of f under those circumstances. Well, when x is equal to 0, the first term is certainly 0. And when z is equal to 0, the second term is also 0. So in this cell, the first two terms are definitely 0. However, in the third term, x is equal to 0, y is equal to 0, z equals 0 would make the last term here, this x prime, y prime, z prime, would be equal to 1, ANDed with 1, ANDed with 1. And so, in fact, we would get 1. And 1 ORed with anything is 1. So in this first cell, we need to put a 1. Now, let's look at the next cell. In fact, we can reason as follows. The whole top row of cells corresponds to x equals 0. And so in the entire top row, we really don't have to worry about this first term, the x, y prime, z term, because x will be equal to 0 in each of these cells on the top, and so that means that this term will drop out. So let's consider just the second term and the third term. Now for the in the 0, 1 cell, this means again, x is 0 and y is 0, z is 1. So if we try that out for this function and look in particular at the second term here, if x is 0 and y is 0, then x prime will be 1, y prime will be 1, and we have z is 1, so again 1 ANDed with 1, ANDed with 1, so we get a 1 in that cell. And that is because the function is equal to 1 in this cell because x is 0, y is 0, and z is 1, and with those particular values of the variables, this term will be equal to 1, so we don't even have to check the rest of f because this is 1, and therefore f itself is equal to 1. Now let's go to the next one. Well, we've already said that the first term is 0 because x is 0. And now we have y is 1 and z is 1. Well, if y is 1, then since this term has a y prime in it, that will be 0, and 0 ANDed with anything will be 0. So the second term will be 0, and for the same reason the third term will be 0. And of course we've already said that because x is 0, the first term is 0. So in this third cell, the one right here, under that combination of the variables, f is equal to 0. Now generally in a Karnaugh map, we don't put down both 1s and 0s. There's some cases when we'll put down 1s, and there are other cases where we'll put down 0s, but we generally don't put down both because they're not necessary. We know that wherever, like for instance in this case where we're already putting down 1s, if we don't mark down anything, we know that needs to be a 0. Or if it's a case such as some of the ones we'll do later where we write down 0s, then in those where we don't write down a 0, we know that's supposed to be 1. So we don't write down both usually. That just sort of clutters up the picture. We'll write down only one or the other. And don't worry at this point. You'll know whether you want to write down 1s or 0s a little bit later. So don't worry about that. But anyway, in this third cell, we have 0, and so we won't write that down. And in the fourth cell, we can reason as follows. Since, once again, the first term, as we said, the first term is 0 over the entire first row. The second term in this cell will be 0 because z is equal to 0. And the third term will be 0 because y is equal to 1. And so y prime would be 0. So the function is also 0 under these circumstances right here. And now we're ready. We've checked all the cells on the first row. Now let's check the cells on the second row. Okay? When x is 1 and... Okay, well, let's make the following observation that will make this very quick. When x is equal to 1, x prime is 0. So along the entire bottom row, the second term will be 0, and the last term will be 0, because both of those terms involve x prime, and x prime is equal to 0 when x is equal to 1, and 0 ended with anything is 0. So we don't have to worry about these last two terms at all for this last row. We only need to look at the first term. And so when x is 1, y is 0, and z is 0, this first term will be 0 because z is 0. And so the function is 0 in this first cell, and again, since the function is 0, we don't write down anything. Let's go to the next situation. When x is 1, y is 0, and z is 1, well, if x is 1, y is 0, that means y prime is 1, and z is 1. 1 ended with 1 ended with 1 is 1. So in this case, the function is 1. Now we go to this situation. Since y is equal to 1 in this cell, 1 prime is 0, and 0 ended with anything is 0, so f is 0 here. And finally, in this case, since z is equal to 0, this term is 0. And there we have it. This right here is the Karnaugh map for the given function. Now, that doesn't tell you why the Karnaugh map is useful. It doesn't tell you how the Karnaugh map can be used to simplify a function. We'll get to those topics in just a few minutes, but for right now, the main thing is to know how to fill in a Karnaugh map, and you can see how it's done as we proceeded just there. And I'll say one more thing. This probably seemed rather tedious, but actually you'll get much faster with it, because you'll be able to just look at each term like this. If the function you have is written in a sum of product forms, as this function is, then you'll be able to look at each product and pick it out on the Karnaugh map very quickly, and so the process will be much faster than what we did here. So let's look at another example, and we'll see how one could do this a little bit more quickly. So let's say g of x, y, z is equal to x, y, z, or x prime, y prime, z, or maybe x, y prime, z prime, or x prime, y, z prime. This is a good example. And so once again, this is a function of 3 variables, and therefore we're going to have 8 cells in the Karnaugh map. And once again, I'll label the vertical axis as x. The horizontal axis, I'll have y and z. 0, 1, 0, 0, 0, 1, 1, 1, 1, 0. Now it's very important that you remember that ordering. If you don't remember the ordering, the Karnaugh map will be useless to you. So it's very important. Okay, so let me show you now how we could do this a little bit more quickly. Okay, we know that looking back at one of the ideas we looked at earlier, we know that each one of these products is an implicant of G. In other words, when this first product is 1, G will be 1. When the second product is 1, G will be 1. When the third product is 1, G will be 1. And the fourth product, when it's equal to 1, G will be 1. And in fact, one of these products, well, let's just say these are the implicants of of G. And so since we know that when any of those is equal to 1, G will be 1, this will give us a very quick way to fill in the Karnaugh map for G. So let's look, for instance, at x, y, z. That is only equal to 1 in one of these cells. And I hope that you can quickly see that that cell is this one, the 1, 1, 1 cell. When x is 1 and y is 1 and z is 1, then g will be equal to 1. And so we put a 1 here. X prime, y prime, z. When is that equal to 1? Well, in the case 1, 1, 0. And 1, 1, 0 is right here. You see it's x equals 1 in this bottom row, and in this column y is 1 and z is 0. So 1, 1, 0 corresponds to this cell in the lower right hand corner. For the third term, x, y prime, z prime, well, we want 1, 0, 0, and 1, 0, 0 is over here. And finally, x prime, y, z prime, we want 0, 1, 0. And 0, 1, 0 would be up here. We have x is 0, and then y is 1, z is 0. And that's it. And so you see that we can indeed, as was claimed before, we can fill in the Karnaugh map very quickly if we look at these terms in the right way. Now let's look at still another example. Let's say maybe h of x, y, z. And this time we'll have a little twist in it. Now I want to, before we, well, let me go ahead and give the example and then we'll let's look at this example. Again, this is a function of 3 variables. So we have a Karnaugh map with 8 cells. And we'll label it just as we did before. Now I think immediately you're probably looking at this expression for h, and you're probably hesitating a little bit about x and y because there is no z there. So how do we proceed? Well, you notice, let's look at our previous problems. You see, in the examples we've looked at so far, this is a min-term expansion for f. And each one of these min-terms corresponded to exactly 1, 1 in the Karnaugh map. So since we had 3 min-terms, we had 3 1s. Likewise here, this is a min-term expansion of g. We have 4 min-terms in this expansion, and there are 4 1s in the Karnaugh map. But in this case, for h, we do not have a min-term expansion. And therefore there's a question. Well, how many 1s will we have in the Karnaugh map in this case? Now, I hope that you will immediately realize that one way of solving this problem is the following. We can get a min-term expansion. And of course, to do so is very easy. We know that xy is the same thing as xy ended with 1, which is the same thing as xy ended with z or z prime. And then, of course, the other 2 terms are already min-terms, so we don't need to alter them in any way. X prime, y prime, z, or x, y prime, z. And then when we expand this out, we'll get x, y, z, or x, y, z prime, or x prime, y prime, z, or x, y prime, z. And now that we have a min-term expansion, it's easy for us to fill in the 1s on the Karnaugh map. this first term x, y, z, we need 1, 1, 1. That is, when x is 1, excuse me, I filled in the wrong one there. Right here. When x is 1 and y is 1 and z is 1, as is the case in this cell, then the function h must be 1 because this first term is equal to 1 under those circumstances, and 1 ORed with anything is 1. Let's look now at the second term. In fact, I really strongly encourage you to turn off the video for a moment and try to fill in the rest of the Karnaugh map for this function. Then resume. Okay, I hope that you found out that for the second term, we go to the 1, 1, 0 cell, which will be here. X is 1, y is 1, z is 0. So 1, 1, 0 here. For the next term, 0, 0, 1, which would be here. X is 0, y is 0, z is 1. And finally, for the last one, 1, 0, 1. So that would be here. X is 1, y is 0, and z is 1. So you can see that this, in this case, this function here, which has just 3 terms in it, actually will correspond to a Karnaugh map with 4 1 cells. Now, there's a new bit of terminology. A cell that contains a 1 in it is called a 1 cell. And so in this case, we see that the second term corresponds to 1 1 cell. The last term corresponds to 1 1 cell. But the first term actually corresponds to 2 adjacent 1 cells. The 1, 1, 1 cell that we picked up from this first term, and the 1, 1, 0, this one, that we got from the second term. But both of these terms here came from our first term, x, y. So this is an interesting observation. If you have a min term in your functional expression, if you have a SOP expression, sum of products, then any expression there within it, any term that is a min term, will correspond to just 1 cell. But smaller terms, in other words, ones that don't contain as all of the variables, will actually correspond to more 1 cells in a Karnaugh map. Let's look at still another example now. Let's maybe say J of x, y, z is equal to x, or we'll say x prime, y prime, z prime. So once again, this is a function of 3 variables. So our Karnaugh map will have 8 cells. And we could, we have the same situation as we did in the previous problem. We do not have a min-term expansion. And therefore, the problem here is that this first term is simply x. It doesn't have a y in it, and it doesn't have a z in it. So this is certainly not a min-term. And you know that the way that we would get it to be a min-term is to AND it with both y or y prime and z or z prime. And so that would lead to 4 terms. And now this is a minterm, and so it will correspond to only 1, 1 in the Karnaugh map, but we expect to get 4 terms now out of this. Well, we could do all this expanding that we're talking about, but I'd like to now show you a faster way to do it. And it goes as follows. For this to be equal to 1, all we require is that x is equal to 1. So anywhere in the Karnaugh map that x is equal to 1 should get a 1, because if x is equal to 1, then j is equal to 1. In other words, x is an implicant of j, and therefore wherever x is equal to 1, j must be 1. So in this entire second row, j is 1. And notice, sure enough, that gives us the 4 cells corresponding to the 4 minterms we would get if we ANDed x with y or y prime, and also with z or z prime. So these are the 4 cells that we would get. And I encourage you, if you have any doubt about that, to check it out. And then finally, what about x prime, y prime, z prime? Well, that will be equal to 1 in only one case, and that is when x is 0 and y is 0 and z is 0, which corresponds to that cell. So this function will have a Karnaugh map with 5 1 cells. And I'd like to point out one more thing to you. The shorter the term is, the bigger its representation on the Karnaugh map. What do I mean by that? Well, x is the shortest term we've seen in all these examples. X is the shortest term, and it knocked out an entire row of 1s. The next shortest term was xy, and remember, it gave us half a row. It gave us these 2 1s. But a term with 3 variables in it corresponds to just 1 cell. So this is an interesting thing to remember. The shorter the term is over here in your functional expression, the larger it will appear on the Karnaugh map. In other words, the more 1s you will need to fill in. Now, before concluding this lecture, I'd like to show you one more idea, which is the following. Let's suppose that instead of having an algebraic expression for our function, we have it in decimal notation. So, for instance, let's suppose we had f of x, y, z equals the sum of the minterms 0, 2, 3, 5, and 7. And we want to know the Karnaugh map for this. Well, this is actually very easy. As usual, we begin with the observation that we have 3 variables, so we will have a Karnaugh map with 8 cells. And as usual, we will label the vertical axis with x and the horizontal axis with y and z, and we'll fill in our numbers, being careful once again on this top. Say 0, 0, 0, 1, 1, 1, 1, 0. Now, you might be thinking that what you need to do is to get the algebraic expression for f, and then to look at each one of those terms separately. You know that the good thing here is that f is already in terms of minterms. In fact, we have 5 minterms. We have minterm 0, 2, 3, 5, and 7. So we have 5 minterms, and you know that each minterm will give you exactly one cell. So you expect to have 5 1 cells in this problem. And you might be tempted to say, well, I want to find the algebraic expression Once I found the algebraic expression, I can look at each term individually and then decide which cell that corresponds to. But if you do that, what you'll notice is the following. There's a much simpler way to do it. 0, for instance. Well, 0, min-term 0, remember, that corresponds to the binary number for 0, which is 0, 0, 0. And therefore, min-term 0 just gives us a 1 here in this cell. Likewise, 2, how do you express 2 in binary? 0, 1, 0. And therefore, we get a 1 there. 3 is 0, 1, 1. So we have a 1 here. What about 5? That's 1, 0, 1, which gives us a 1 here. And 7 is 1, 1, 1, which gives us a 1 here. And it's just that simple. So you can see from that, and let's go ahead, just in case you have any doubt, let's show that this is true. So if you did use the method I suggested at first, which is to go ahead and get the algebraic expression, okay, we're going to have 5 min-terms, so I'll go ahead and write out x, y, z, x, y, z, x, y, z, x, y, z. Or x, y, z, because we know that every min-term must have all 3 variables in it, and there must be 5 of them, so I'll denote it like that. And then for 0, well, we can do it like this. This is 0, 0, 0. 2 will be 0, 1, 0. 3 would be 0, 1, 1. 5 would be 1, 0, 1. And 7 would be 1, 1, 1. And now if you want to put the primes, you know that anything that has a 0 gets a prime. So this is x prime, y prime, z prime, x prime, y, z prime, x prime, y, z, x, y prime, z, and the last one just remains x, y, z. So there's your algebraic expression for f. X prime, y prime, z prime, or x prime, y, z prime, or x prime, y, z, or x, y prime, z, or x, y, z. There's your algebraic expression. And now, following the procedure we had before, you want to find the circumstance that will make each one of these equal to 1. Well, the circumstance that will make the first one equal to 1 is 0, 0, 0. So when x is 0 and y is 0 and z is 0, this will be 1, and if that's 1, then f must be 1. And so therefore, for 0, 0, 0 cell, we must put in a 1 for f, and voila, there we have it. Likewise, for this one, we want x to be 0, y to be 1, z to be 0, because that would make this term 1, which would make f 1. So we go to the 0, 1, 0 cell, 0 for x, and 1 and 0, and that's this one. For this one, we would have 0, 1, 1, and 0, 1, 1 is right here. For this one, 1, 0, 1, which corresponds to this, and then finally 1, 1, 1, which corresponds to this cell. In fact, you will quickly learn how to actually count in the Karnaugh map. Let me show you what I mean by that. If you always remember to associate the x digit first and then these two, okay, this is 0, 0, 0. So this is 0, 1, skip the next one, 2, 3. Again, let me make sure you understand. This is 0 because we have 0, 0, 0. This is 1 because we have 0, 0, 1. We skip over to here. This is 2 because it's 0, 1, 0. And finally, this is 3 because we have 0, 1, 1. Then 4 comes down to here, 1, 0, 0. 5. Skip again, 6. And then come back, 7. So again, 0, 1, 2, 3, 4, 5, 6, 7. If you learn to count in the Karnaugh map like that, it will help you to do these problems very quickly, particularly when you have min-term expansion given for the function in decimal notation. It's just very, very quick. And so now let's look at a couple of problems on Karnaugh Maps. So now we finish up this lecture by looking at the two problems. Problem 10.1 says, for which of the given functions is this the Karnaugh map? So we have a Karnaugh map here, and the functions A, we have x prime y prime z, or x prime y z, or x y prime z. For B, our choice is x prime y z, or x prime y z prime, or x prime y prime z prime, or x y z, or x y prime z. For C, our answer is x y or z prime, and for D, it is x or y or z. One of these functions does correspond to this Karnaugh map. Which one is it? And similar question down here. For which of the given functions is this Karnaugh map? You see a Karnaugh map here, and you have you have 4, A, B, C, D. You have 4 min-term expansions here. Each of them is given in decimal form, or equivalently, we could say in the little m notation. One of these is the correct expression for this Karnaugh map. Which one is it? So that concludes Lecture 10, and good luck.